Hi, my name is Mike lUlrey. I am retired from Boeing and I'm interested in some topics in quantum physics, specifically Bell's theorem. This talk is a continuation of last year's talk, an update of the research I've done in the last year. Thank you very much. My name is Mike lUlrey and I am retired. I used to work for Boeing and I used to give talks on what I worked on at Boeing. Now I have a hobby, and that hobby is trying to understand some nice physics, fun things I wanted to do always when I was an engineer but didn't have the time. So I'm not a complete novice, but I'm not a professional physicist. Never was, I was an engineer. But anyway, these topics interest me. And in particular, I'm interested in quantum physics and the foundations of quantum physics, in particular Bell's theorem, which has all interested me for a long time. And last year I gave a talk on this. Some of you may have been here. Hold up your hand if you heard my talk last year. Anybody? Okay, all right. So this won't be too much of a repeat then. But anyway, I've done some work since then that I would like to report. And Mathematica has been extremely helpful in being able to do stuff like, with pencil and paper, it would have been impossible to get to this point. So it's really wonderful to have a tool like this to get things better understood. So let's see if, there we go. Trying to do the touchpad here. Usually I use the mouse. So I'm going to tell you what this talk is about and not about. It's not going to be about all this stuff, only one small part of it, mainly down here where we have the aspect experiment, and we're trying to understand good models for the aspect experiment. I'm not going to talk about the EPR paper or their original Gedanken experiment where Einstein was worried about quantum theory getting away from what he thought physics should be. It should be about real stuff out there that you do experiments and you can determine what that stuff is. He didn't like the idea that the observer was starting to have a role that it shouldn't have and things didn't appear until the observer looked at it. He didn't like that. He and Bohr debated that for years and years, even before the paper and then after the paper, and then it kind of went into a limbo kind of thing. And then in 1964, Bell took Einstein's argument, or the EPR argument, and kind of turned it on its head and said, if I assume the things that Einstein assumed, I can come up with an inequality, which is a falsifiable by experiment. The technology had caught up, and he came up with a falsifiable statement that experiment could decide was true or false. He had a simple inequality, which is illustrated in this box at the lower right-hand corner. And then several experiments were done before 1982, but the clincher was the 1982 one, which kind of confirmed what Bell said. Basically, if you assume locality and reality in some sense, then you get a model that is unable to make predictions that quantum mechanics can make, some predictions that quantum mechanics can make. And this led to more experiments. I think in 2015 there was the final experiment to end all the loopholes, the detection loophole, the fair sampling theorem loophole, fair sampling loophole, and all these kind of loopholes that statisticians and physicists had worried about. And then there's been all kinds of debate. There's been debates about what Bell actually proved, what Einstein actually said. It goes on and on and on. You get all these different formulations and interpretations. The multi-universe interpretation of quantum physics, the pilot wave theory of de Broglie-Bohm of quantum physics, and the debate, the growth of ideas and formulations keeps going to this day. I mean, it's amazing how many papers come out every year that cite Bell's paper, thousands of them. So my job in this, my goal in doing this project was to kind of understand what Bell actually said in terms of what did he assume mathematically that locality meant? What did he assume mathematically that reality meant? And does that have anything to do with our common sense everyday concept of those ideas, of those words? So that's what I was trying to get to. And first of all, let me just briefly say how the aspect experiment is done. This is just an abstract picture, the plus ones and minus ones coming out as results. So you see outcomes were really numbers involving Planck's constant and pi. But you can, since there's only two outcomes, you can assume they're plus and minus one if you rescale everything. So everything in this paper will be plus or minus one. So just assume all the physics is rescaled. So Alice is at one laboratory, Bob is at another laboratory. They're separated by a huge distance, and they can only do things in their own laboratory. They can't see what's going on in the other one. And Alice has two measurement angles. Say they're measuring photon polarizations, the polarization of photons, entangled photon pair. One of the pair goes to Alice, the other pair goes to Bob, and Alice does a measurement on her part, and Bob does a measurement on his part at different angles of their choices. And Alice doesn't know Bob's angles, and Bob doesn't know Alice's choice of angles. Then you get plus or minus one coming out of Alice's experiment, out of Bob's experiments. They go to a coincidence monitor. Don't ask me how that happens at the moment because they're separated by a large distance. That's another issue for another day. But let's assume that you can compare those and you get either perfect correlation, plus, plus, minus, minus, or perfect anticorrelation, plus, minus, or minus, plus. Then you put them into bins according to which choice of angle settings they made, either A for Bob or A prime for Bob, A for Alice or A prime for Alice, B for Bob or B prime for Bob. So you have 4 bins, you add up all the plus ones and all the minus ones, and then you do a correlation estimate by subtracting the number of minus ones in each bin from the number of plus ones and putting it over the sum of all the samples. And then that becomes a correlation estimate. And then you do certain things with those correlations, which I'm going to explain in a moment. First of all, you might have an example set of outcomes as follows. You have a large number of capital N trials. I've shown 10 here. Notice there's only one plus or minus one in each row. That means they can only have one setting at a time, either AB prime, A prime B, or AP, B prime, B prime. There's no more than one row, one or minus one per row. So in each column, you add up all the ones and all the plus ones, all the minus ones. For example, in the first column, N1 plus and N1 minus, similarly for the other columns. And then you compute the correlations, as I explained before, the difference between the pluses and the minuses over the sum of the pluses and minuses in each column. And then you compute what's called, what I'm going to call an S function, an aspects description of his experiment. He called it S. He took the correlations, he added them up, but put one minus sign in there in all the 4 possible ways. So there's 4 possible S functions. So these become estimates of those S functions, S1 hat, S2 hat, S3 hat, and S4 hat. Those are crucial. Those are crucial to the difference between what quantum mechanics can predict and what a real or local model can predict or can't predict. So keep in mind those S functions. I'll tell you what they are later on too, so don't worry about that. But in any case, it turns out that this is a little bit of words I just said. Well, I didn't say it quite as detailed as this. But it turns out that the S functions, by Bell's assumptions, can only, his inequality says these can only be between no more than 2 and no less than minus 2. Whereas quantum mechanics predicts that there are some situations where you can get as low as minus 2 times the square root of 2 and as high as plus 2 times the square root of 2. And a Bell real or local model cannot do that. So something's going on here. You have to, Bell said you got to pick 2 out of 3. You can have realism, you have locality, you can have quantum mechanics. Pick 2. You can only have 2. You're going to have to give up one of them. And that's the essence of Bell's theorem because of a simple inequality having to do with probability. And I wanted to understand exactly what those assumptions were made were. By the way, I'm going to use not Bell's original theorem, but a paper that came later in 1969, Clauser, Horn, Shimoni, and Holt. That's where CHSH comes from. They had a generalization of Bell's inequality. So my approach in doing this was to define or to assume a set of random variables. A is capital A is Alice's outcome, capital B, Bob's outcome. D of capital A is Alice's detector setting. D of capital B is Bob's detector setting. And the deltas are the probabilities of the 4 different combinations of detector settings, 2 for Alice, 2 for Bob. And this is the key to my whole starting point in trying to understand it. I posited a generic model, 16 possible outcomes for the 4 random variables, which can each take +1 or -1, and a PMF, a probability mass function, where the gamma k's, gamma 1 through gamma 16, are conditional probabilities that given that detector setting, you get that outcome. And the deltas, of course, are the probabilities of the detector settings to begin with. So this is a conditional probability times a detector setting probability. And so all those 16 numbers, if you think about it, add up to 1. And they're non-negative and add up to 1. So it's a probability mass function, given the constraints on the right. All right. Now, oops, sorry. Yep, sorry, next one. Okay, locality. What are the definitions of locality? That's the problem with the understanding Bell's theorem is, and the whole debate about it is there's at least 4 different definitions of locality. And that's why I wanted to straighten all this out. You've got remote context independence. That means that Alice's outcome only depends on her detector setting, not on Bob's detector setting. That's the first one, RCI. The second one, and similarly for Bob, the second one, remote outcome independence. That means that Alice's outcome does not depend on Bob's outcome given the 2 detector settings. Similarly for Bob, that's ROI. Local causality is even stronger. It says Alice's outcome as conditioned on Bob's outcome and the 2 detector settings ends up being the same, exactly the same as probability of Alice's outcome given her setting. You can throw away Bob's outcome, you can throw away Bob's detector setting. That probability doesn't depend on those 2 things. That's a really strong independence. And then the last one, the really strong one, well, it turns out to be equivalent to local causality, is kind of a conditional independence statement. The probability of Alice and Bob, joint probability of Alice and Bob's outcomes given their detector settings is equal to the conditional probability of Alice's given her detector setting times probability of Bob's outcome given his detector setting. It's kind of a conditional independence sort of thing. So you've got those 4 definitions of locality. They're kind of floating around, you got to straighten out. And that's what I tried to do in this presentation, in the paper I've written on this topic. And reality has to do with the idea that what Einstein says, if you're telling me quantum physics is right, something's going on here, there has to be something sent to Alice and something sent to Bob, hidden variables, like 2 outcomes, A1 and A2 sent to Alice, and she gets A1 if she chooses her first detector setting, gets A2 if she chooses her second detector setting, similarly for Bob. And that's what's really going on. That's what Einstein would like to think. And then that leads to, I show in my paper, which isn't published yet, I'm trying to get it published. If anybody wants to give me help on that, I'd appreciate it. If you start with the A1, A2, B1, B2 and assume a row 1 through row 16 probability distribution, that turns into the A, B, D, A, D, B format on the right. On the left is what, Bell actually, and Clauser, CHSH actually assumed. On the right is my reformulation of that. And I've not seen this reformulation on the right anywhere. This is kind of new as far as I'm concerned. I haven't seen that kind of thing in any papers, but it's equivalent to the one on the left, just in a different arrangement. So remember, that's what reality means in the CHSH or the Bell assumption of what reality means. Just that. It's just mathematics. That's all it is. So now you have, I discussed 5 main modeling types so I can compare how each one performs in terms of the S function output. And there's 5 conditional probabilities. Notice I've dropped the detector settings. These are just the gammas for the generic, for example. The 4th column over, the generic model or maximal model. You'll see why I call it either one in a moment. The gamma k's can be anything, although 4 of them have to add up. There's sets of 4 that have to add up to 1. That total column will add up to 4. Each column will add up to 4 in each case. There's 16 output. Oops, what happened here? Not very good with the touchpad. There we go. Okay. And then the constraints at the bottom are these. The 5th column over, the quantum mechanics, are just the predictions of the standard Hilbert space theory. Not except, but I also have a constraint that the last 3 angles, measurement difference angles have to sum up to the first one. And I'll show you why that is in a minute. The next column over are the Bell-Rhee conditional probabilities. Those rho k's have to add up to 1. And then the Bell local is the next to the last column, where the alpha k's are Alice's conditional probabilities, the beta k's are Bob's conditional probabilities, and the overall joint conditional probability is just the product of those two. It's exactly what locality means. And then the last column is what I call the trivial model. It just says everything's 1/4, a completely uniform distribution. Not a very interesting model, but it kind of indicates a minimum, just like the generic model is the maximum. And the reason for the angle, measurement angle thing, theta 1 equals theta 2 plus theta 3 plus theta 4, just look at this diagram. You have Alice's angles A and A prime, Bob's angles B and B prime, and the difference angles. And by the way, in quantum theory, the outcomes of the measurements only depend on the difference between the angles. That's why you define the thetas. And you notice in this particular picture, theta 1 is the sum of the other 3. Now that could be a different arrangement, but you can always make it look like this, so we'll just assume that. Then the correlations for each of the model, they're conditional correlations of products. Alice's measurement times outcome times Bob's outcome, A times B, which will always be plus or minus 1, based on 4 different detector setting combinations. So you have 4 different correlations you can compute. And this is the table of what they look like. You have the generic ones, the first column, then the QM ones, which are cosines of 2 times the difference angles in each case. The Bell-Rhee ones, which are plus or minus sums of all the rho k's. And then the Bell locals are the interesting products of Bob's and Alice's conditional probability. Minimals is trivial, they're all 0 because it's uniform. There's no correlation at all. And then the CHS inequalities, Clauser, Horn, Shimoni, and Holt, that wrote the paper in '69, says that those inequalities say that all 4 of the S functions have to be between -2 and 2. That's that paper. You can also read it in a class, in any textbook on quantum theory. You happen to pick one book that I know the author of. That's what the CHS inequality looks like. Then you get Bell's theorem in a nutshell. Compute all the S functions, compute their maximums and mins. First column, QM, the maximum min are plus 2 and plus 2 times square root of 2 down at the bottom. Read the bottom row. The bottom row, the maximum min, you know, is 2 times square root of 2, and QM, Bell-Rhee and Bell local, plus 2 and minus 2. What that tells you is that the S functions you get from assuming locality reality cannot recreate all of the predictions of quantum mechanics. Some of them, but not all of them. The extreme values of the quantum mechanics ones are higher than the Bell-Rhee or Bell local ones. That's essentially what Bell's theorem is telling you, if you assume reality or locality. As a picture version of this, I like a lot, based on the angles, the green square is the limit of the Bell predictions, which is 2. That's at a height of the green square is a height of 2. The very curvy yellow surface, that's the S1 function, by the way. This is all the S1 as a function of the measurement angles. The yellow surface is the quantum mechanics S1 function. Now, it's mostly below the square, so they agree down there. They could agree. But above that, they can't possibly agree. And the example that's usually cited in the literature, the notorious angles of 22.5 degrees, 22.5 degrees, 22.5 degrees, and 67.5 degrees, is the purple dot at the top. That's where the quantum mechanics S1 function reaches the value of 2 times the square root of 2. And that can't possibly be done by a Bell-Rhee model. So that's another way to look at Bell's theorem, pictorially. And here's a summary of the results from the work I did. I mean, some of this is old news, but some of it, by my definitions, is kind of interesting and a different way of looking at things. All Bell local model instances, these are instances. These are meant to be model instances. You put in actual numbers. The set of all such models for Bell local is strictly contained within the Bell-Rhee models. QM intersects the Bell-Rhee models. They're in a non-empty subset, an infinite subset, but only Bell local. The only QM model that's also Bell local is just one, the trivial model, the one with 0 correlations, which is not very interesting, of course. So it doesn't mean much. And then there's the deterministic model types, and this is something new I haven't seen anywhere. I was able to determine there's all these, the deterministic, well, first of all, what's deterministic? Deterministic means that all the parameters in that table I showed you at the beginning, like the gamma k's or the rho k's, they all have to be 0 or 1. They can't be anything in between, just 0 or 1. What that means, it makes the correlations all plus or minus 1. That is, everything's either perfectly correlated or perfectly anti-correlated. This is what Einstein was looking for way back in 1935. He said, what happened to determinism? What happened to being able to tell something's really there, that I can really tell you what it is? And that's why he proposed originally a deterministic kind of, he said the random or the hidden variables should be deterministic. So that's why everybody considers those as well. In my situation, I can decide, or it can divide them up into 4 different types. The inside type 1, there's only 16 instances of those, and those are all Bell-Rhee and Bell-Local. All the other 3 are not either Bell-Rhee or Bell-Local, yet 2 of them satisfy the CHS inequalities. That is, they can't predict all of the predictions or recreate all the predictions of quantum theory, which is kind of interesting. In other words, it's not satisfying the CHS inequalities is the necessary condition, but not sufficient for this. Oh, I just ran out of time, didn't I? So what should I say here? I guess that's, well, oh, I want to show you one last thing, and then okay. This is my favorite part of the things I was able to do, because this finally helped me understand all the relationships between all of the concepts, all of the models, all of the conditions that people talk about in the quantum theory paper, or the foundational quantum theory papers on Bell-Rhee and Bell-Local and all that, Bell's theorem. All of those things I was able to put together in this chart and show how they're all related to each other. So you'll see, for example, Bell-Local feeds into Bell-Rhee. Every Bell-Local model is built Bell-Rhee. Quantum mechanics and Bell-Rhee both feed into remote context independence, which is very interesting. They're supposed to be different. Quantum mechanics is touted as non-local, but it goes right into remote context independence, which is a local concept, just like Bell-Rhee does. And notice that all the boxes outlined in red are all the types of models or conditions that satisfy the CHSH inequalities. That is, cannot recreate the predictions of all the predictions of quantum mechanics. So since I ran out of time, I better leave it at that. Thank you very much.